Hi, I'm imos. Let's get started. Today I'd like to talk about weather forecasting and imos method. They are researches that I studied in university, and weather forecasting. Yeah, today today presentation consists of two topics. One is weather forecasting using optical flow, which is I researched it for my bachelor degree, and the other one is cumulative sum with higher order and a dimension, which I researched for my master degree, and the latter one is also known as imos method between competitive programmers in Japan. Yeah, because I like the algorithm and I told the algorithm to many people. As a result, they call it imos method. And yeah, the first one is weather forecasting. I proposed weather forecasting by detecting optical flows on precipitation radar images, and what's difficult in weather forecasting is according to chaos theory, weather has a chaotic behavior. As a result, the uncertainty in the forecast increases exponentially with the elapsed time. And then, in other words, the short-term weather forecasting should be exponentially easier. But yeah, I think it's not enough for now. And why currently the short-term weather forecasting is not enough accurate is I think that the currently Kishocho, Japan Meteorological Agency, provides weather forecasting, but it uses numerical fluid simulation. That is using radar images and sensor data like temperature or pressure and so on. And based on them, they estimate the every block of on the air of the air on the Earth, and they'll run this fluid simulation. And after that, based on the result of the fluid simulation, they predict the futures precipitation. And I think that predict indirectly. And plus the numerical fluid simulation has another problem, which is the computation is very heavy. Now, actually, the Kishocho still runs only every 30 minutes for numerical fluid simulation. And Kishocho provides short-term weather forecasting like every 5 minutes, but that is based on the numerical fluid simulation and the latest radar images. Using the based on the airflows of numerical fluid simulation, and so the airflow is not accurate in terms of short-term forecasting. And plus, the latter one is that I said before. Numerical fluid simulation needs many estimation like temperature, pressure, and humidity, and but the sensors are not dense enough to estimate all the blocks in the Earth, and so it has much uncertainty. And the proposed method uses only radar images to predict radar image, and then so it can predict directly. And simply calculate the optical flow of the current radar images, current and past from the past radar images, and it just extrapolate the optical flow and make it as a prediction. And the optical flow algorithm that I used was the something somewhat different from the measure algorithms. And then currently there, of course there are many more better algorithms, but the two major algorithms were the Lucas-Canady method and Horn-Shanks method. The Lucas-Canady method cannot estimate the optical flow as dense space, and so it's not so useful for forecasting. The latter one can estimate the optical flow for dense space, but it's not enough because it's too sensitive to noise. And so I propose a method that uses the alternative of Horn-Shanks method, like using image patches instead of using it just comparing pixel by pixel. And this is one result. The left one is ground truth, and the center one is Kishocho's result, and my method is the right one. For example, the Hiroshima ken, the left red circle, there is a mountain here, and air flows comes from north to south, and but there is a mountain, so the airflow can go over mountains, but rain clouds they cannot go over mountains. So as a result, the Kishocho's method moves the rain cloud over the mountain, and but my method detects optical the air cloud flow can be stopped can be prevented by the mountain from the past images, and as a result that can predict more precisely. And the same thing happens around Wakayama-ken. And there are other observations, and there are many small whales in a big field. One typhoon can have many whales inside, and that can the bigger whales prediction. But optical flow detection with longer term, like I used 60 minutes past data for 20 minutes prediction, while 180 minutes data for 60 minutes prediction. And then the longer data can ignore small changes, and as a result, the optical flow can improve the result. And plus the proposed method can easily predict expansion and shrink of clouds, but the existing method, the physics simulation cannot estimate the expansion of clouds because the air flow can itself does not expand or shrink, but the cloud can be expanded and shrink, and the optical flow just sees only cloud flows. Therefore, my method can easily predict them. And plus, I think the current UXs are not intuitive enough for users. that who want to know weather forecasting of a few hour future at one place, like at here or something like that. The short-term prediction can be provided like the left one, and but maybe people don't know where they are in the map, and so it's not intuitive. Plus, the pinpoint weather forecasting does not provide real-time information because they use only the numerical fluid simulation results, and therefore they are not updated. They are updated only every 3 hours or something like that. And my proposal was like this one, and it shows one place weather forecasting, and it shows every minute forecasting. And as a result, weather forecasting with higher precision comparing to Kishojo, and enabled weather forecasting within 1 minute with 250 meter grids using expanded MP radar, which is the most precise radar data in Japan, and it can be calculated on VPS. And I provided weather forecasting service for areas around universities, and there were thousands of users. And the other topic was is cumulative sum. I proposed when I was a master's student, I proposed a fast, flexible wavelength transform method using cumulative sum with higher order and dimension. The basic idea is very simple. This is an example of zeroth order 1D cumulative sum. If we want calculate the sum of a range of 1D data, you can calculate it, have a cumulative table that calculated beforehand. In this example, if you want to calculate the red range, and then you can calculate it as orange box minus green box. And it can be extended to two-dimensional space. And if you want a red area, and then you can also calculate it as orange boxes minus green boxes. It can be if you want to calculate it naively, and then you can you need to calculate it in the computational time in order the proportional to the area size, but it can be in constant time. And additionally, it can be extended to higher order. For example, this is second order example. If you put 1 there, and then by calculating cumulative sum 3 times and one different operation, and then you can get like 1, 4, 9, 16, 25. This is square numbers. And then plus I come up with an good polynomial approximation for some the functions that are used by wavelet transform. This is this is Gaussian function. It can be approximated by this equation. It just have only 4 control points, and the Gaussian, the true Gaussian function is red, blue line, and the approximation function is red line. They are very similar, and so they can enough used for wavelet transform. And plus, the Gaussian function is very interesting. The Gaussian function can be rotation free on two-dimensional space, and of course, my approximation can approximate very precisely, and so it can be extended to the two-dimensional field. And this is this shows elevations, and approximation is red, and the Gaussian true Gaussian function is denoted by dotted line, and as a result, I can give rotation-free features by 16 multiple operation and operations. Basically, that's it. I propose the method calculate wavelet transform sparsely in time and calculate wavelet transform incrementally. That's it. Thank you. Any questions?
Is anyone using your optical flow for weather forecasting now?
Oh, sorry.
Is anyone using it now? Like your research is done, but do you know of any other agencies or anyone that's taken it up?
Not yet. Yeah. So one of my dream is to use the algorithm to forecasting, and so yeah, I wanna do it in this company later.
Okay.
I heard that Japanese weather prediction is actually pretty well compared to worldwide. So, do you can predict such weather prediction for worldwide, or you need data set or actual 観測したなんかセンサー値みたいなのがないと日本みたいなやつはできない。
Yeah, partially. Yeah. Basically, true. That's true. The why the Japan's the prediction accuracy is high is that the radar is very good, and yeah, actually, I've never heard that there are many radars that can detect 1 minute and 200-meter meshes, and so yeah, if we put such radars on the other countries, and then we can do it.
Is it possible to なんか衛星データとかでなんとかなったりしないですか？公開されてるやつ。難しい。
どうかな？I have no idea, but yeah, of course, we can improve many method, many data, and so I think we can have better results than the simple fluid simulation.
Thank you very much.
So do you use the echo intensity, or do you also use the echo height? So do you ignore the height of the cloud?
Currently, ignore everything, and so they are predict directly.
Interesting. Thank you.
Do you have an API for the weather forecasting program? Through Amazon Echo.
Yeah, I provided it before, but the data source is closed. After that, I didn't restart it yet, but I want to do it in the near future. Any other questions? Thank you.